Last time we looked at how to do an initial rates problem, how you could figure out what the rate law is dependent on the initial concentrations of different substances and how the rate changed depending on what those concentrations were. Today we're going to look at a couple of different examples where rate isn't necessarily dependent, or we're going to look at the ways that it's not dependent on concentration, but rather dependent on time. So let's look at some different types of rate laws. So that initial rates type of rate law idea is often called the differential rate law, or we'll just call it rate law. We'll make it just easy. And this is what we've looked at so far. It's how rate depends on, remember those square brackets mean that that's going to be the concentration of our reactants. Or we can talk about how rate is a function of time. I said that wrong. How rate is a function of concentration. There we go. How rate is a function of concentration. This next part, we're going to look at what are called integrated rate laws, which talks about how concentration depends on time. But these are a little bit trickier to mess with. In fact, you actually derive the equations from calculus, and you know how much I just love calculus. So we're going to keep this part pretty simplistic. We're going to just look at first and second orders, and we actually have equations, and then we just plug stuff into the equation is how this is more or less going to work. So let's look at some of these types of equations you might see. Now, integrated rate laws depend on what the order of the reaction is. So we're just going to be looking at first orders and second orders. So here's the first one we're going to look. This is an integrated first order reaction. So if we look at our basic rate law, it says rate is equal to K. Remember, K is our constant, times the concentration of A. A is one of the reactants, and it turns out it only depends on that one reactant. And we're going to see how that concentration of A depends on time. Now for this, we have this great equation. It says the ln, so that's natural log. So we haven't worked too much with natural log, but it's a button on your calculator is what you just need to know about for right now. And you can see that this is the concentration of A naught. So this is your initial concentration over your final concentration. And if you take the natural log of that ratio, it equals K. Again, that constant times T, which is your time. The time will depend on the problem itself. It could be in seconds or minutes, and K will actually tell you what that time will be measured in. Now, this equation, it can get a little bit hairy sometimes. So what I've done is I've actually rearranged the equation for you. So look at this second one. If you're trying to find your final concentration, it's a lot easier to use that second equation. If you're trying to find the time or the K, use the first equation. So make sure that both of these are written down on your cheat sheet card. So if we're going to be solving for the final concentration, the concentration of A after some point in time, that's going to be equal to your initial concentration times E. Now, E is also onto your calculator. And if you look really closely at your calculator, what you'll notice is that log and 10 to the x are inverses of one another. Natural log and E are also inverses of one another. So your E is just the base system of natural log, and it starts off with 2.718. It's a button on your calculator. Don't make it any harder than you need to. Now, the other thing I could do is I rearranged the equation one last time. And this last way that I have it rearranged actually looks at the slope of a line. So we could say that y, do you remember the slope of a line, or the equation of a slope? Yeah, that whole thing, the equation of a line. Y equals mx plus b. So in case you're curious, m is going to be our slope. And then B is the intercept of that. Yeah, brings in all sorts of stuff. Now, the other thing that we like to do in chemistry is we like to have graphs with straight lines. So if we want to graph this data and end up with a straight line, you would have to plot the natural log of A, the natural log of the concentration, versus time. So that's a good thing to remember because I think there's some questions in sapling that are going to go over this. So let's see what that would look like. All right, so here we have two graphs and we are plotting different bits of information. And again, we're trying to find a straight line because we love straight lines. The first one is the concentration of A. A in this case happens to be N2O5 versus time. Now, whenever you write those titles, we actually have the x-axis that's listed first, in this case the concentration, and we see how it is a function of time, which is our independent variable along the bottom. The second graph that we have is the natural log of A versus time. And we see that this one's actually preferred because we have a straight line. So if you have a first order reaction, you want to have the natural log of A versus time for whenever you plot it.
Like this guy?
Okay, so here's the problem that's going to be looking at integrated first law. It says dinitrogen pentoxide is not very stable. It can decompose as follows, and it has the reaction. Now remember, you cannot predict the rate law based on the coefficients. Instead, it actually tells you what the rate law is. The rate is, there's the rate law, K times concentration N2O5, and notice that it has no exponents, meaning that this is a first order rate law. So we can use our integrated first order equations that we just looked at. At 45 degrees C, now was temperature anywhere in there? No. Now your rate law, your K, will depend on what the temperature is, but we're not going to use that in the equation. The rate constant for this reaction is 6.22 times 10 to the negative 4th seconds to the negative 1. Rate constant, that means that this is going to be your K. If the initial concentration of N2O5 in the solution is 0.1, so this is, and I'm going to use that generic A here, this is your initial, so it's A naught. How many minutes? So we're trying to figure out what is the time in minutes. Okay, you got to be careful because that's minutes and the K was in seconds. So something to keep in mind. How many minutes will it take for the concentration to drop to 0.01? So this is my concentration after a certain amount of time. All right, so try the problem. I'm going to, go on to the next slide, and I'm actually going to try to work this one out. All right, so let's try that problem. So a couple of things from the other page. Let's see here. Let's write down, that basic equation, because this was an integrated first order, there we go, first order rate law. This is the equation that we're going to be using. We have the natural log of A naught over A after some sort of time is equal to K times T. Now we're going to be solving for T. I found it's easiest for me if I go ahead and rearrange the equation and then come back and actually plug in my numbers. So that T is going to be the natural log of A naught over A final, or A after time, divided by K. Now remember, we identified what all those variables were on that last page. So let's plug them in. So we have time equal, we have the natural log of the initial concentration was 0.1 molar. The final concentration was 0.01 molar. And then all of this was divided by the time. Now that time, and I probably should have made a little note of this. I'm sorry, it's not divided by time. What am I talking about? It's going to be divided by K. Oh, that's what I get for trying to look at too many things here. 6.22 times 10 to the negative 4th. And then this is seconds to the negative 1. Now, one of the most common mistakes I see is just not being able to put this into your calculator correctly. It's a pain because it's a natural log. And depending on how your calculator is set up, you might have to solve that portion first before you take the natural log. Or maybe you don't. figure out your calculator. Also notice on that bottom when you divide by the k, it is times 10 to the negative fourth, so make sure your calculator realizes what you're trying to do. Now, whenever you plug this all in, you should end up with something like 3,700, assuming that my math is right. Units on this, the molarities have canceled. That's seconds to the negative 1 because it's on the denominator. It comes to the top. If you want to see how to kind of switch those units around, let me know later. It's going to be in seconds, 3,700 seconds. And then we go back and say, okay, is this what we're looking for? And the problem did ask for the time, but it asked for the time in minutes, not seconds. So we have to take this one more step. We're going to say, all right, there's 3,700 seconds times. All right, how do you go from seconds to minutes? There's 60 seconds in 1 minute. So when you divide that, it should give you something like 61.7 minutes, something like that. All right, any questions you have, make a note of them. Ask me later. All right, we have one more problem to try here. So this is the second part of that big problem. It says if the initial concentration is 0.5, so that is going to be the concentration of A at time 0. What will its concentration be? So that means that we're trying to figure out what is the final concentration, or what's the concentration at time whatever. And then it says after exactly 1 hour. So this is my time. Now, for this one, because we're actually going to be solving for a final concentration, it's a little bit easier to use the other equation that we were given. Let's see here. Let me flip back in my notes to look at that other equation that we were told. This one is going to be, let me write it down here. The concentration after time is equal to the initial concentration times E to the negative KT. Now, in the previous problem, we were told what K was. And the thing about that is we have to make sure our units will match. The K was in seconds to the negative 1, meaning our time needs to be in seconds. But it's not. It's in hours. So let's go ahead and make a quick conversion. We can say that 1 hour, let's see here, there's 60 minutes. And in every minute, there's 60 seconds. So that's 3,600 seconds. Okay, there we go. All right, so now we have all of the parts so that we can go ahead and enter it into this equation. What we can say is that, let's see here. Our initial concentration given in the problem is 0.5. That's in molarity if you needed to know that. E to the negative. Then we're going to put our K in here. That K was 6.22 times 10 to the negative fourth. And then our time is 3,600 seconds. I didn't put units in that one. Well, okay, I did on the seconds. On the K, it was seconds to the negative 1, so they would actually cancel out. My advice here, take as many steps as you need to go ahead and solve the math on this. You might need to go ahead and figure out first those numbers on top, multiply those together, and then take the negative of that, and then take E to that. Yeah, you know what I'm talking about. What you should end up with is 0.053 molar. So go ahead, try the math. Again, if you have questions, just let me know.